This is a video on trigonometric substitution. Let's take a look at an example. Suppose we have the integral of x squared divided by the square root of 9 minus x squared dx. Now, if it helps us, we can write this as the integral of x squared divided by the square root of 3 squared minus x squared dx. Now, let's draw a right triangle to help us with our substitution. So here's my triangle, and we'll call this angle theta. And notice how we have a square root of 3 squared minus x squared in the denominator. What that dictates is the following. My hypotenuse, which is the side opposite to the 90-degree angle, is going to be 3. And notice how I have the square root of 3 squared minus x squared in the denominator, which tells me x will be the length of one of the legs. And so I'm going to let x be the side opposite, the length of the side opposite to angle theta, which tells me that the side adjacent to angle theta will be the square root of 3 squared minus x squared. Now I'm ready for my substitution. So according to the triangle, we know that x over 3 is equal to sine of theta. Multiply both sides by 3, and we get x equals 3 sine theta. Dx is 3 cosine theta d theta. Okay? Now, from the right triangle, we also know that the square root of 3 squared minus x squared divided by 3 is equal to cosine theta. Multiply both sides by 3, and we get the square root of 3 squared minus x squared is equal to 3 cosine theta. So the integral of x squared divided by the square root of 3 squared minus x squared dx is equal to the integral of, now remember, we'll put a note up here, x is equal to 3 sine theta. Okay, x is equal to 3 sine theta. Dx is 3 cosine theta d theta. Now, let's put in our information here. I'm going to take x and square it. And when I do, I get 9 sine squared theta. Okay? And square root of 3 squared minus x squared is 3 cosine theta. And so I'm going to divide by 3 cosine theta. And then dx is 3 cosine theta d theta. So I'm going to put that over here. So I want you to notice 3 cosine theta and cancels out that 3 cosine theta, right? And I'm going to pull the 9 out in front of the integral. And so we end up with 9 times the integral of sine squared theta d theta. Recall, sine squared theta is equal to 1/2 of 1 minus cosine 2 theta. And so 9 times the integral of sine squared theta d theta is 9 times the integral of 1/2 of 1 minus cosine 2 theta d theta. I'm going to pull the 1/2 out in front as well, and that makes 9/2 when I do. So I get 9/2 the integral of 1 minus cosine of 2 theta d theta. And so this is 9/2 times the quantity, theta minus 1/2 sine 2 theta plus c. Okay, now sine 2 theta is 2 sine theta cosine theta. Now, let's plug that in. So this is 9/2 of theta minus sine theta cosine theta plus c. We're not done. Now remember, sine theta is x divided by 3. Therefore, theta is arc sine of x over 3. Okay? And then cosine theta, if we go back, is square root of 3 squared is 9, by the way. So cosine theta is square root of 9 minus x squared divided by 3. And so, therefore, the answer is 9/2 times the quantity arc sine of x divided by 3 minus, and then I get x square root of 9 minus x squared divided by 3 times 3, which is 9, plus c. Now, you can distribute the 9/2 inside. That's fine. If you distribute the 9/2 inside, you get 9/2 times arc sine. Let's write that a little cleaner. Of x over 3 minus, and then if I multiply 9/2 times that second term, the 9's cancel, and I get x square root of 9 minus x squared divided by 2 plus c. And that works as well. And that's how we do the first example. Let's take a look at another example. Suppose I give you the following. Suppose I give you 1 over the square root of x squared plus 2x plus 5 dx. So what I need to do is complete the square. And so I'm going to write this as the integral of 1 over the square root of. Now, I'm going to group the first 2 terms together, okay? And then I'm going to have a 5 on the outside here. And so I have x squared plus 2x, right? If I want to complete the square, there's a dx there, I got to take half of 2 and square it. And when I do that, I get 1. But I can't just add 1. I have to subtract 1. Okay? And so if we come over here, we can write this as the integral of 1 over the square root of x plus 1 to the second plus 4. Now, if it helps, my suggestion is to do a u substitution. So we could look at this a little cleaner. I'm going to let u equal x plus 1. du is 1 dx. And so what we end up getting is 1 over the square root of u squared plus, now remember 4 is 2 squared, du. Draw a triangle. When you have a sum of squares, that dictates that you have the, you know the lengths of the legs of the triangle. So, in other words, I'm going to let the length of the side opposite to angle theta be u. And I'm going to let the length of the side adjacent to angle theta be 2. Now, does it have to be in that order? Technically, it doesn't. But it's more convenient to deal with tangents than it is to deal with cotangents, shall we say. Now, the hypotenuse is the square root of u squared plus 4. Okay? 2 squared is 4. Now, the triangle dictates that u divided by 2 is equal to tangent theta. So u is 2 tangent of theta. du is secant squared theta d theta. The square root of u squared plus 4, right? And I'm going to divide by 2. And that's equal to secant theta. So the square root of u squared plus 4 is equal to 2 secant theta. So I'm ready for my substitution. So 1 over the square root of u squared plus 4 du is equal to the integral of, now I'm going to get 1 over, right? The square root of u squared plus 4 is 2 secant theta. Okay. Now remember, u is equal to 2 tangent theta. So there should be a 2 here. So du is 2 secant squared theta d theta, right? So I'm going to multiply this by 2 secant squared theta d theta. And so this is the integral of secant theta d theta. And so this is equal to the natural log of secant theta plus tangent theta plus c, right? But remember, secant theta is, if we go back, is square root of u squared plus 4 divided by 2. Tangent theta is equal to u divided by 2. And so this is natural log of the square root of u squared plus 4 plus u divided by 2 in absolute value plus c. But I can write this in the following way. This is natural log of the square root of u squared plus 4 plus u minus natural log of 2 plus c. This can get absorbed. That natural log of 2 with the negative can get absorbed into that constant. And then if I put back u, remember u is equal to x plus 1. And so this is natural log of the square root of x plus 1 squared plus 4 plus x plus 1 in absolute value plus, we'll call it C1. Now, to be complete, we should write it this way. This is natural log of the square root of. Now, we're going to get x squared plus 2x plus 5, right? Plus x plus 1 in absolute value plus c. And I called it C1. So we'll stay with that. And that's how that one works. Let me show you one more. And I will show you this one. Suppose I had the integral of the square root of 1 plus x squared divided by x dx. Draw a triangle. Now, here's angle theta. Here's my right angle. We have two legs because it's a sum of squares inside the radical. So the side opposite to angle theta is x. The side adjacent to angle theta is 1. The Pythagorean theorem tells me that the hypotenuse is the square root of x squared plus 1. Let the triangle dictate the substitution. Okay? That's the name of the game here. So x over 1 is equal to tangent theta. Dx is secant squared theta d theta. The square root of x squared plus 1 is equal to secant theta. Okay? I hope that makes sense. Now, let's come over here. So this is the integral of, now I'm going to replace the square root of x squared plus 1 with secant theta. Okay? I'm going to replace x with tangent theta. And then I'm going to multiply by secant squared theta d theta. Now, the typical way to do this problem is I'm going to take secant squared theta and I'm going to write it as 1 plus tangent squared theta. So in other words, I have secant theta over tangent theta times 1 plus tangent squared theta d theta. Okay? Distribute. When I distribute, I get the integral of secant theta over tangent theta plus secant theta tangent theta d theta. Now, this second term is really nice. It's this first term we have to deal with. Now, I'm going to write the first term as cosecant theta. I claim that that's cosecant theta. So this is the integral of cosecant theta plus secant theta tangent theta d theta. And so this is natural log of the absolute value of cosecant theta minus cotangent theta plus secant theta plus c. Now, let's go back to the triangle. Let's remind ourselves. So we have x1, the square root of x squared plus 1. Now, cosecant theta is square root of x squared plus 1 divided by x. Cotangent theta is 1 over x, okay? And secant theta is the square root of x squared plus 1. All you have to do is put it together. And so this is natural log of the square root of x squared plus 1 minus 1 divided by x. Okay? They have the same denominator, so that's okay. Plus the square root of x squared plus 1. That's what secant theta is. And then we just have to add that c at the end. Okay, that'll conclude this video on trigonometric substitution. And we did 3 examples. Okay, thank you.